Good morning everyone, and welcome to today's worked exam answer question, where we're having a look at 3 different organic reactions that are all linked to reduction. So we have this one here where we're changing NO2 groups into NH2 groups with the presence of a benzene ring. In part B, we're looking at how we're going to go from a benzene ring to a cycloalkane. And then the final question on the back, we're looking at the reduction reaction involving NABH4 from this ketone here to this alcohol, going for the mechanism and explaining why the product of that reaction is optically inactive in relation to the mechanism. So although not linked specifically, they are all linked together by the fact that they are reduction reactions. We will see a lot of organic questions like this where they draw upon lots of different reactions and mechanisms all in the same question. So very good practice for that. As always, I'm going to go through and highlight the key points and do my answers, and I will explain them all to you as soon as I have done that. Okay, so first up we're having a look at the conversion from a benzene ring with 2 nitro groups, which is the NO2s, into a benzene ring that's then got 2 amine groups on it. We're asked to identify a reducing agent, to then write a balanced equation for the reaction, in which we're going to use this square brackets in H for the reducing agent, which is pretty common, and we might use a square bracket with an O for an oxidizing agent. And we've been asked to work out and use the molecular formulae for the nitrogen containing compounds, which is what I've done there for the 1,4-dinitrobenzene, and I've done here for the 1,4-diaminobenzene. We then need to draw the repeating unit of the polymer formed by the product of this reaction with benzene 1,4-dicarboxylic acid, which I drew out here. The polymer that we're going to get between this diamine and this dicarboxylic acid is a condensation polymer. We're going to be losing water, and we need to know which atoms are removed when we do that, which I've annotated down here. So we can make amines in different ways, and when we're trying to make an amine where the NH2 group is on a benzene ring, we have to do that differently from when we're making an amine where the NH2 group is just on our standard sort of carbon chain. The reducing agent for this is hydrochloric acid, and we would do that with a tin catalyst, and we would heat under reflux. Neither of those points are relevant, but just wanted to mention them for other questions. So it's the H from the HCl, which we're going to have in our square brackets here. So essentially we are taking the oxygens off of the nitrogens and we're replacing them with hydrogens. So we're going to need 1, 2, 3, 4 hydrogens for that. And then the oxygens also react with hydrogen to make our second product, which is water. So for each oxygen that we're then removing, we're going to need another 2 hydrogens, which is where the 12 here comes from. And then there's my repeating unit. So when you are making a condensation polymer, it is always the OH that comes off of the carboxylic acid group. If it was an acyl chloride you were using, it would be the Cl that came off. And then when we're using a diamine or a diol, it is always one of the hydrogens that comes off of the amine group and the H that comes off of the OH. That then generates us this, which is our amide linkage in the middle. We need to show the continuation bonds out the side because it's asked us for the repeating unit, and then what would happen is another one of the diamino monomers would join on to the left hand side, and another of the dicarboxylic acid groups would join on to the right hand side. So we'd get this the amide linkage, which is the same as a peptide bond, repeated over and over and over again. So that was worth 5 marks, and actually because they asked about condensation polymers, they've thrown in an additional sort of organic reaction in there as well. And like I said, that's very common for them to ask about lots of different content at the same time. Okay, on to the next one. Okay, so here's our second conversion. We're taking our benzene ring and we are hydrogenating it. So we're flooding it with hydrogen to break the ring of delocalized electrons and give every carbon a second hydrogen. So because it wanted the empirical formula of the product, I've annotated on here the molecular formula of the benzene initially, the molecular formula of the cyclohexane that we've made afterwards, and then empirically we just need to simplify that ratio of 6 to 12 to 1 to 2. So the empirical formula of the product is CH2. There's a couple of ways we can do this. We can either use hydrogen with a nickel catalyst, or we can use LiAlH4 dissolved in ether, which is our solvent. Either of those is fine. I think hydrogen's a bit easier to remember, particularly in this instance because we are literally flooding with hydrogen to get rid of the ring of delocalized electrons and ensure that every carbon is forming its 4 bonds. Now that also helps us think about the bond angles. So we've been asked for the bond angle between the carbon atoms in the starting material versus the bond angle between the carbon atoms in the product. So I've tried to draw these little diagrams here. So this would be our benzene ring where the carbons are each bonded to 2 others, and then each carbon only has 1 hydrogen and the final electron, which exists in a p orbital, which is then overlapping with the other p orbitals to create that delocalized ring of electrons. That electron is therefore not used in a bond. So each carbon atom in benzene is only bonded to 3 things. So that's going to mean it's going to have a trigonal planar shape, and thus the bond angle both between the carbon and the hydrogen and the carbon and the other carbons is going to be 120 degrees. If the idea is that we are then breaking open that delocalized ring of electrons and giving each carbon another hydrogen, when we get over to the product, the shape is going to then be tetrahedral because we've got carbon bonded to 2 other carbons and to 2 hydrogens. So each carbon then has 4 bonding pairs of electrons, and with a tetrahedral shape, the bond angle between the carbon hydrogen bonds and the carbon-carbon bonds, and between the carbon-carbon and other carbon-carbon bonds, is going to be 109.5 degrees. And I have seen other questions where they will use organic reactions to get you to think about whether the shape of the reactant and product is different, and thus whether the bond angles are the same or different. So I would suggest it is a good idea to not only get used to doing bond angles with inorganic species, but to also be comfortable with the idea of doing it with lots of different organic products as well, where you might have trigonal planar shapes, you might have tetrahedral shapes, and understanding when and why you have those. And finally, we were having a look at how the reducing agent NABH4 was used in the following conversion. So we've got a ketone there because the seedable bondo is in the middle of my chain, and I have reduced that down to an alcohol, and that is a secondary alcohol because the OH group is on a carbon that is bonded to 2 others. We have to name and outline a mechanism for the reaction. So this is nucleophilic addition, and we need to be able to spot that. And if you're struggling, have a look at the difference between the reactant and the product. We have added a hydrogen onto the oxygen and a hydrogen onto that carbon. We have not taken anything away, so we've not substituted, we have not eliminated, we have added 2 atoms on, so it has to be addition. And we're going to do that using a nucleophile, and the nucleophile comes from the NABH4, which is the hydride ion, the H- ion, and it has to be H- because hydrogen as an atom only has 1 electron, so we need to gain an electron to give it the lone pair, which means it can then attack the carbon of the seedable bondo. And when we're thinking about nucleophilic reactions, we need to have a polar bond with a partially positive charge that the nucleophile is going to want to attack, which might be the C of a seedable bondo, or in nucleophilic substitution, it's the C of a carbon halogen bond instead. So the hydride nucleophile attacks the delta positive carbon, and the C double bond O breaks one of those bonds with the electrons going to the oxygen atom. So nothing is being removed in that first step, and it can't because we're doing addition. That's going to leave us with this intermediate where the oxygen that was originally double bonded to the carbon now has a negative charge and a lone pair, which it uses to grab a H plus ion, which is going to form our alcohol group there. This hydrogen up here is the hydride ion that we used as the nucleophile. And it is not necessary for you to draw the product of this reaction because there is only one potential product of this mechanism. Some people like to do it because they feel the mechanism is incomplete to stop there, and I understand that. I would be the same, but I have to issue a word of caution because if you were to accidentally draw that product wrong for whatever reason, let's say you missed out a CH2 and you did it as propan-2-ol, you would then be penalised a mark even though you don't get a mark for drawing it. So please just take care. That's why it's in the highlighter brackets. The reason I drew it is because it links into our next question, which is asking us to, by considering the mechanism, explain why the product formed is optically inactive. Now, there's two reasons why a product may be optically inactive. It might have no chiral carbon, which means it would have no effect whatsoever on plane polarized light because there would be no optical isomers that we could even draw. Or it can be optically inactive by showing no net effect on the plane polarized light because we do have a chiral carbon and we do have optical isomers, but those optical isomers are made in an equal amount, so we don't see that net effect. The plane of the light will be rotated, but it will be rotated one way by a certain degree and then would be rotated back again by that exact same degree. So by drawing the product, we can see that we do have a chiral carbon. It's that second one there that I've represented with the asterisk, which is fairly common. That is a chiral carbon because that carbon is bonded to 4 different atoms or groups of atoms. We've got the hydrogen, the CH3, the OH, and the CH2CH3. So that is my chiral carbon. So therefore, we need to explain why this mechanism must therefore be producing a racemic mixture. Now, the carbonyl group, the carbon double bond oxygen, when it is bonded to 2 other things, is planar, i.e. flat. This means that the H- nucleophile can either attack from above the plane and kind of approach the carbon from the top end, or it can attack the carbon from underneath and sort of come up from underneath and attack the carbon from behind. Those are equally likely. If our C double bond O is planar, then the nucleophile, doesn't care which side it attacks from. Probability tells us that that is equally likely. And if we had the nucleophile attacking from the top, that's going to give us one of our optical isomers. And then if we have it kind of coming in from the bottom, that actually forms our other optical isomer. They would be mirror images of each other, and because the attack by the nucleophile is equally likely, we get this racemic 50-50 mixture of the 2 optical isomers, and that has no net effect on the plane of the plane polarized light, which would suggest that our product is optically inactive. Those marking points would get you all 3 marks, which is what that part of the question is worth. It does come up quite often by reference to the mechanism, and it's really important that you don't just say the CO bond is planar. You have to say it's the whole carbonyl group, which would insinuate the carbon is then bonded to 2 other things, because it's only when we think about it in this trigonal planar shape, to link into the question beforehand, when we can realise that that is planar and flat, and that's what then leads the nucleophile to attack both above and below. Hopefully I've explained all that really clearly, but if there's any part of this question that you think, oh, I'm not too sure about that, please do not hesitate to leave a comment on the video or reach out to me via social media or email. I'm always really happy to explain anything that might be unclear. Likewise, if anybody has any special requests, please let me know. And I look forward to creating another video for you soon. Have a good day, guys.